Hi guys, so today we're going to take a look at question 8 of paper 2 of the 2016 exam. Okay, so the height of the water in a port was measured over a period of time. The average height was found to be 1.6 meters. The height measured in meters, h of t, was modeled using the function h of t equals 1.6 plus 1.5 cosine pi over 6t, where t represents the number of hours since the last recorded high tide, and pi over 6t is expressed in radians. And it wants us to find the period and the range of our function. Okay, so we have this function that measures the height of the water. H of t equals 1.6 plus 1.5 cosine pi over 6t. Okay, and we're looking for the period of this function. Okay, so we have, whenever we have a function of the form a plus b cosine ct, or a plus b sine ct, the period, we have this formula for the period. The period of this function is 2 pi over c. And a formula for the range of values that it hits, is a minus b to a plus b. Okay, so let's just use this formula to answer this question. So in our case, a is 1.6, b is 1.5, and c is pi over 6. So if we plug that into our formula for the period, we get that the period of h of t is 2 pi over pi over 6, which is just 12. So the period of ht is 12. Okay, and then if we use our formula for the range of ht, a is 1.6 minus b 1.5 to 1.6 plus 1.5, or 0.1 to 3.1. So that is our period of h and the range of h. Now on to part B, find the maximum height of the water in the port. So we're looking for the maximum of h of t. And now the typical way that we would go about this, whenever you see maximum in regards to a function, you should immediately be thinking derivative. You find the derivative of h of t, so derivative and second derivative is a negative. So you want to find where the derivative is 0 and second derivative is negative. So that's, when you hear maximum, that's immediately what you should think. And then you would find that value of t, and then you would plug that into the function, and then you would get the maximum height. But in this case, we don't need to do all that because we already have the range. So the range is 0.1 to 3.1. So the range is the set of values that the function attains. So so the height of the water goes all the way from 0 to 3.1. It takes values in that range. And so the maximum value there is, of course, 3.1. So we have this sort of trick way to do it, since we've already calculated the range. And that sort of makes sense, because if we look at the function h of t, we have a cosine, and so we know that cosine can only be as large as 1. So when this is biggest when cosine is 1, and when cosine is 1, the function is 1.6 plus 1.5 times 1, which is just 3.1. So that's why in this case we can just use the fact that the range, we've already found the range. But usually derivative and second derivative is 0 and second derivative is negative is the way to go for a maximization. Now on to part C. Find the rate at which the height of the water is changing when t equals 2, correct to 2 decimal places. Explain your answer in the context of the question. Okay, so first of all, let's find the rate. So again, we have our function h of t, the height of the water with respect to t equals 1.6, or as a function of time, cosine pi over 6t. And so we want to find the rate of change of the height of the water. So we're looking for dh dt, the rate of change of height with respect to time. Okay, so to do this, well, we're just going to differentiate our function h of t. So if we differentiate h of t, h prime of t, well, the 1.6 will go away, and we'll get 1.5 times the derivative of cosine, which is just minus sine pi over 6t. And then we have to multiply this by the derivative of t, because it's the chain rule. We have a function pi over 6t within the function cosine. So we have to use the chain rule. So the h prime of t is 1.5 times pi over 6. So that's just 3 over 2 by pi over 6, which is just pi over 4 times minus sine pi over 6t. So this is our derivative of h, and so we're looking for the derivative of h when t is 2. So h prime of 2, we just plug in 2 here, so minus pi over 4 sine pi over 6 by 2, so just pi over 3. And if we plug this into our calculator, we get minus 0.68. Okay, so that's the rate at which the height of the water is changing. And so what does that mean in the context of the question? So in the context of the question, so the rate of change of the height of the water is minus 0.68. So the height of the water is decreasing. So the height of the water and it's decreasing at a rate of 0.68 meters per hour, because that's the units that we're working in. The height of the water is decreasing at a rate of 0.68 meters per hour. Now you could here say something about the tide is going out and the water is decreasing, but it's probably just fine to just say the height of the water is decreasing at this rate in these units. The important thing here is to put it into like an English sentence. Now on to part D. On a particular day, the high tide occurred at midnight, so t is 0. Use the function to complete the table and show the height ht of the water between midnight and the following midnight. Midnight and the following midnight. Okay, so they've told us that t equals 0 at midnight. So if we plug that, so let's go back to our function. H of t equals 1.6 plus 1.5 cosine pi over 6t. And when t equals 0, well, cosine of 0 is, well then we'll have 0 in here, and cosine of 0 is 1, so we'll just have 1.6. So for t equals 0, we get 1.6 plus 1.5 times 1, so we just get 3.1. And with this makes sense because they've told us that it's high tide at this time. So this is 3.1. At 3 a.m., t equals 3. So let's plug in t equals 3 into this formula. So we get 1.6 plus 1.5 times cosine pi over 6 times 3. Cosine of pi over 2, so this whole thing is 0. So we get 1.6 plus 1.5 times 0, so just 1.6. 1.6 after 6 hours, when t equals 6, we get 1.6 plus 1.5 times cosine pi over 6 times 6. So just cosine of pi, which is minus 1. So we get 1.6 plus 1.5 by minus 1. So that's just 0.1. And that makes sense. 6 hours after high tide is usually low tide. So it makes sense that we get 0.1 here. Then after 9 hours, t equals 9, we get 1.6 plus 1.5 cosine pi over 6 times 9, which gives us 3 pi over 2. And cosine of 3 pi over 2 is again 0. So we get 1.6 plus 0. And then after 12 hours, well, we could plug this in, but we actually know that the period of this function is 12. So after 12 hours, it will be the same thing it was 12 hours ago. So it will be 3.1 again. And then after 3 hours, 12 hours after 3 a.m., it'll be the same, 1.6. After 18 hours at 6 p.m., 12 hours after 6 a.m., it'll be 0.1. And so you can see it just repeats. And now you could do this all out you could continue for t equals 12, t equals 15, but because we know that this is a function that repeats, it has a period, we can just do it this easier way. And then it wants us to sketch the graph of ht between midnight and the following midnight. So at midnight it is 3.1. At 3 a.m. it is 1.6. At 6 a.m. it is 0.1. At 9 a.m. it is 1.6 again. And then at midday it is 3.1. And then it repeats 1.6 at 3 p.m., 0.1 at 6 p.m., 1.6 at 9 p.m., and again 3.1 at midnight. So then if we connect these like a sine function, so something like, not like that. So something like this. And now it doesn't really matter that you're super precise, but that you have this type of curve is really the only thing that matters here. So something, as long as it looks broadly like this, it should be fine. Because if you remember, a cosine or a sine curve, they look something like this. So it's just a stretched out one of those. And now on to part E. Find from your sketch the difference in water height between low tide and high tide. Okay, well this is just very simple. High tide happens here. Low tide happens here, and high tide happens here. And so the difference, well, we know that this is, from a guess, from looking at the graph, it looks like it's about 3. And then we know that the top is 3.1 and the bottom is 0.1. So we know that the difference is 3 meters. So 3 meters between high tide and low tide. That's a very nice question, very easy marks to pick up. So on to part F. A fully loaded barge enters the port, unloads its cargo, and departs some time later. The fully loaded barge requires a minimum water level of 2 meters, and when the barge is unloaded, it only requires 1.5 meters. Use your graph to estimate the maximum amount of time that the barge can spend in port without resting on the seabed. So we're looking for the maximum amount of time that the barge can enter the port at over 2 meters, and then it stays below 1.5 meters for as long as, stays above 1.5 meters for as long as possible. So for example, let's say if he went in at 3 a.m. Well, it's at 2 meters, so he can get in just fine, or let's say a little bit before 3 a.m. So it's over 2 meters, but then he has to leave by here. So he got in at, let's say, 2 a.m. and they've got to be gone by like 3:30. So they would only have like an hour and a half. So doesn't seem like a very good solution. Whereas if he got in at, let's say right at, a little bit past 9 a.m., then he could stay all throughout this time. He's good, still good, and then he's good all the way until about here. Or no, sorry, here. So he can stay for this whole time. And so, well, he can stay till about, is that a little bit past 3 p.m., I think? Just like a little, they can stay a little bit past 3 p.m. So in this case, he got there at about a little bit past 9, and I keep saying he, I don't know why. The barge can stay there until around a little bit past 3 p.m. So around 6 hours, maybe slightly less. So let's say 5 hours and 50 minutes. And if we look at the graph, we'll see that there's no longer period of time that the barge can stay longer than this, a little bit less than 6 hours.